Alrighty, before we begin, a few announcements. Homework 1 has been posted to the course website. We're going to talk about that a lot later today, and I'm hoping to give you some time at the end of class to kind of start forming groups and maybe even get a little jump start working on that homework assignment. So we're going to talk about that a lot later. I also did set up a discussion forum, Piazza, for this course. So if you go to the website, there should be a new link up here called discussion. If you click on this, it should take you to Piazza, which is basically a message board is what we're going to be using it for. I do this in a lot of my classes. It's a great tool. So use it if you want to. Don't use it if you don't want to. It doesn't matter to me. It's nice to have it there, but you will have to enroll first. So you'll probably get an enrollment screen here instead of what you see on my screen, right? So let's see, is there any other announcements? I don't think so. We'll talk a lot more about the homework assignment in a little bit. Before we get to that, I want to introduce a topic that will actually be on the first homework assignment. So I'm going to start with this slide deck over the memory mountain for starters today. So memory mountain is kind of a fancy name that we use for writing cache-friendly code. So if you look, we've got two different chunks of code here that only differ very, very, very slightly. In fact, the only difference between the two is the loop variables. They get switched, right? That's the only difference between these two chunks of code. But that one small switch actually has a very significant effect on the performance of this code. So in order to understand what that performance is, cache. So how many of you are familiar with how cache works in a system? How caching works? Awesome. A lot of you are, some of you are not. So let's go through it in a little bit more detail. Caching, the way caching works is periodically I'm going to have to read stuff out of memory, right? But when I read a set of data out of memory, I'm not just going to pull in the stuff that I need. I'm also going to pull in some of the neighboring values, typically. The reasoning for that is this idea of locality, spatial locality. Chances are, if I'm reading a value from a certain memory location, I'm also at some point going to want to read the values in neighboring memory locations. So we can get better performance by loading those values into cache, and that way I don't have to make the trip all the way back to memory, right? Cache is closer to the processor than memory is, so if something is in cache, I can get it faster than having to take that trip all the way to memory to pick it up. So that's spatial locality. There's also this concept of temporal locality, which says if I use a particular value, the chances of me using it again in the future are also pretty high. And so that's another reason why we keep things in cache. As soon as I use a value, I'll stick a copy of it in my cache so that the next time I use it, and the time after that, and the time after that, I can just pull it out of cache without having to take the trip all the way to main memory to fetch that value back, right? And there's multiple layers of cache that we're going to talk about in a little bit. But so in this particular example, we're assuming we've got 4-byte words, right? So if I take a trip to memory, I have to pull stuff back in chunks of 4 bytes, right? And my cache blocks are going to be 4 words long. So my cache blocks will be 16 bytes long. So if we look at this first case, right, this first case, the things that really hurt us here are cache misses. If I go and look up something in the cache and it's not there, that means I have to make that trip all the way to main memory. Those are going to slow us down. So if we look at this first example, right, where I is iterating over the rows and j is iterating over the columns, our cache misses in this case. Can anybody see how often we're going to miss the cache generally? How often are we going to miss our cache in this particular example? Does anybody see? So when we first start, the cache is empty. We're always guaranteed the first time we need to look a value up, we're going to miss. Guaranteed. We're always going to miss, right? So we're going to miss the first value that we try to look up here from our very first row. But when we pull this in, right, we're going to exploit spatial locality. We're going to pull in the next 3 values, actually, from this array and stick those in cache. So that when we move over to the next slot, it might help if I sketch this out. My array is stored as a contiguous block in memory, right? So my first 4 values are in a row. My next 4 values are also in a row. This is what we call row major order. And pretty much every language does it this way. There are some languages that don't, but pretty much every language stores stuff in row major order. So this is my 2-dimensional array, right? It just goes as a contiguous block in memory. When I try to fetch this first value here, I'm going to look for it in the cache, and it's not going to be there. The cache is going to be empty for starters, right? So I make the trip to memory. I'm going to grab this value, but I'm not going to grab just this value. I'm going to say, well, I think that since I'm using this array value, chances of me using the next array values are also pretty high. So I'm going to grab in this entire chunk, right? And this entire chunk is going to go and get put into cache. That entire chunk is going to go. So that when I iterate through the next time, I'm looking for this value, right? It's already in my cache. I've saved myself a trip to memory. I've saved myself time, right? And that's going to be true for this one and this one as well. What's going to happen for this value? It's going to miss, but it's going to do the same thing. It's going to pull in the next chunk, right? And so this will hit, this will hit, this will hit. So do you see the miss rate now? You see the pattern? It's going to be 25%. I'm going to miss 25% of the time under this, right? Which seems like a significant amount, and it is. But let's examine this second example. So this is the same as the first one, right? Except for the variables have been flipped. The loop variables have been flipped. That means I'm now iterating down the columns of the array instead of the rows, correct? But my array is still being stored in the same fashion. My array is still being stored in row major order. So what does that mean in terms of cache? I'm going to go look up the first value, and it's not going to be there. Same as last time, right? The cache is empty for starters. So I'm going to go look up this first value. It's not going to be there. I'm going to pull in the next 3 values in the same row. But I'm not going down the rows anymore. I'm going down the columns. So what's going to happen in the next iteration? I'm going to miss that too. And then the iteration after that, I'm going to miss that one too. And depending on how large my cache is, I'm potentially always going to miss. The miss rate here could be 100%. It depends on how big my cache is, right? So you can see that just flipping these 2 variables has a huge, huge effect on performance. Very noticeable effect on performance. This is really spatial locality in action. We haven't exploited temporal locality at all because we're using each value exactly once. In order to utilize temporal locality, we have to use the same values multiple times, right? So we're using spatial locality here. This is an illustration of how spatial locality can fail. Let's talk about this concept a little bit more. Before we go on, just a couple of definitions. So read throughput, we're going to define as the number of bytes that can be read from memory per second. And that allows us to define this concept of a memory mountain. You'll see why I call it a mountain in a couple of slides here. The memory mountain is going to be throughput as a function of locality. So we really want to try to quantify how much locality actually exists on this system. Can we put a number on that? How can we quantify the amount of locality on our system? What we're ultimately going to show is that for some programs, the performance, the execution time is not dominated by the number of computations, the number of operations. It's dominated by memory performance, right? Because you really can't underestimate how slow those trips to memory actually are. We'll talk about that more later with the first homework assignment as well. So here's how the memory mountain works, right? Here's how this works. We've got a number of elements in our array. This stride is going to change how far we move down the rows of our array. So for example, if I have a stride of 1, I'm going to visit each element, right? If I have a stride of 2, I'm going to start leapfrogging elements. If I have a stride of 3, then I'll leapfrog 2 elements, right? Kind of get the idea. The reason that we vary the stride is because eventually, if my stride gets large enough, I'll hit the point where I'm pulling in a row and sticking it in cache, but the stride is far enough that I'm not reading those values anymore, right? I'm forcing it to determine when the cache will start to miss, right? That's kind of the idea here, is we're stressing this system out. We're trying to find out where those boundaries are, right? When do I start forcing cache misses? Under what conditions do I start forcing those cache misses? Okay, so you can see the stride values used in this loop here, right? And we're going to vary this stride value from very small to very large, and then time the results of this. We'll time the results of this operation so that we can see how those cache misses affect performance on our code. If you do this and then plot the results, you come up with something that looks like this. And now you can kind of see the name, where the name Memory Mountain comes from. Here, on this axis here, this is the stride. Low values are actually up here. So this is a very small stride. This is a very large stride, right? The working set size is how big is this actual array that we're dealing with? How many elements are there in our array? Because caches are limited size as well, right? If I can fit the whole thing in cache, then that's going to be a lot faster than if I can only fit a chunk of my array in cache, right? So over here we see how big is the actual array itself. Again, from very small to very large. And then what we see plotted here is a function of those two based on the read throughput, how much we're reading from memory. And you can see these plateaus. You can see these little plateaus that I've gone and labeled. Cache comes in different flavors. Most machines have at least 2 levels of cache. This particular machine, which was my old laptop, it's actually not even this laptop. It's an old laptop from a few years ago, had 3 layers of cache. So L1, L2, and L3, where L1 is the one that's closest to the processor, the fastest, but also typically the smallest. L3 is the one that's farthest from the processor, so closest to memory, but typically the largest, right? And you can see the specs for that up here. And you can see a couple of things from this trend, right? So as I increase the working set size, eventually I fill up my L1 cache. That's this giant drop-off that you see there. That's that giant cliff that we fall off of. The L1 cache is now too small to fit the array, right? So we have to start filling into L2 cache, and we take a performance hit as a result. It's farther away. And then we see the same thing happen with L3, right? That's going to be a function of our temporal locality, essentially. And then using spatial locality across this axis, you can see there's a general trend that goes down. So our best speeds are up here when the stride is small, because I'm pulling in multiple values, right? So the stride is going to pull in values that will be in cache for us. As I start increasing the stride, I go beyond the values that are being pulled into cache, and I have to make more trips to memory as a result. So you see my performance starts to suffer the larger my stride is, right? It should be noted, you can see the sizes of my cache over here. I have 2 L1 caches, actually a D cache and an I cache. Anybody know what those are for? Instruction and data cache. I have one cache that's just for data. I have another cache that's explicitly for instructions, which doesn't really come into effect here. We're really stressing the data cache in this particular experiment, not the instruction cache. Good. It should also be noted that this is a single-threaded performance. If you increase the number of threads, that kind of changes things as well, right? And so just a few more slides illustrating what this looks like. These are going to be cross sections then. Oh, it cut off the bottom. Sorry. The bottom is the working set size. So how big is the, how much data do we have, right? So you can see this is for a stride level of 12. You can see again as the working set gets larger and larger, the performance suffers as a result. That's a decrease in temporal locality. For spatial locality, whoops, we can vary the stride, and eventually, it's hard to see from this. It's hard to see from this chart, but eventually, what would you expect to happen if I could take this stride out a few more? What would you expect to eventually happen? It would eventually plateau, right? At some point, my stride is just going to be way too large, and increasing it anymore is not going to have any effects because it's already larger than the cache lines, essentially, right? So eventually, it would flatten, but I didn't go far enough in this particular example. Good. So what can we do with this information? If we understand the concepts, that's one thing. What can we do with this information? How can we use this information to our advantage? Well, this gives rise to a technique called blocking. Let's say we want to do some matrix multiplication, which, interestingly enough, is going to be what we're going to be doing on the first homework assignment, some linear algebra, right? So let's say we want to do some matrix multiplication. Here's a very basic matrix multiplication setup, right? This is the way that we would typically do it. We would iterate. We need to do a dot product, right? So one of the rows of this matrix, dot product with one of the columns from this matrix, gives us a value in our result matrix, right? This is the traditional way of doing it. What are we ignoring here? Based on the results that we've seen, what are we ignoring from our results from the experiment? Rhymes with schmocality, right? We're not exploiting any of that locality that I just illustrated. It has a huge effect on performance, right? So we're really not taking it. Iterating down columns, we just showed, is horrible for our performance, right? It has to be done sometimes. I mean, the very definition of matrix multiplication requires it, right? But is there a way that we can rewrite this to limit those iterations? Is there a way that we can do this that will take the size of the matrix into account as well, to try and exploit temporal locality as well? I mean, keep in mind, you know, I'm going to have to reuse this row for the next column, and reuse this row for the next column, and reuse this row for the next column. So if there's a way that I can exploit that information, I should be able to write code that's going to perform more efficiently. So the solution to this is blocking. Here's the same matrix multiplication routine rewritten to utilize blocking. The way that it's going to work is, instead of iterating through the rows of one matrix and the columns of the other, I'm going to choose a block. I'm going to choose a chunk here of this particular matrix. It keeps us from having to iterate down the columns, right? But I can also reuse this block many, many, many times, because I'm going to need this same block of values to compute values over here, right, for all of the different rows and columns of this matrix as well. So I can define a block size. What's going to dictate my block size? What's going to dictate the size of this guy? Cache size. What layer of cache do I want to target? L1 cache is pretty small, usually 32 to 64 kilobytes. But maybe I can target L2 cache. That's usually on the order of a couple megabytes at least, right? That's a pretty significant chunk of space. So, you know, I can write code that will target my L2 cache, have a pretty decent block size, right? And then this entire block is going to sit in cache. And maybe these over here will miss more often, potentially, right? But I'm going to reuse the heck out of that data while I've got it, instead of just tossing it out and moving on to the next column. And you can see that I've also got some row iterations here as well. It's not just purely going down the columns. That's going to give me some cache benefits as well. That's going to be my spatial locality, right? I can exploit that a little bit. And so the code really doesn't change a whole lot. You just have to take into account this block size, which we see here, right? How big is our block size? That will dictate our iteration, our number of iterations. The reason that you see calls to min here are because the block size may not be evenly divisible into our array, right? So at the end, we either have to take the block size or just whatever is left up to n, up to the size of the array. Otherwise, we're going to iterate across in blocks. And then here, when we start entering values into our array, what you'll notice is I'm not computing a single value all in one shot like I was in the previous example, right? And using this code, as soon as these iterations are finished, I have the solution for this, right? I have the solution for this value, the entire solution for it. Here, I'm actually only going to get a partial set of values here. And then when I come back and do the next sliver over here, I'll update these values again and get the next partial value and tally it up. And so only at the very end will I have the final results for all the positions. So it does get a little bit more complicated, right? But it's not that bad. It's really not that bad. And the nice thing about this technique is that everybody can do this. There's no special knowledge necessary. There's no special libraries necessary to do this, right? There's no special tools. There's no special utilities that you need. It's just knowledge of how the cache works. It's knowledge of how your caching system works on your particular system, right? This can be done for every single machine that you've ever worked on. Every machine has cache in it unless you're working on something that's really, really old. In which case, what are you doing? You're in the wrong class, right? What are some of the downsides, though, of this? There are some drawbacks, some challenges, I guess. Is my cache size going to be the same as your cache size? No. So the block size that I choose is going to be very, very platform specific. That's kind of a drawback. I can't write very general code in this manner. That's one of the downsides of this. I really have to have some idea of what the target platform is going to be, which is some pretty detailed information, right? Not just the cache size, but also the cache line size, how much data is being read into the cache in one go. Will this help every single program that you've ever written? No, it won't. Mostly programs that are going to deal with large data sets, large 2- and 3-dimensional data sets in particular, to really gain the benefits out of this. But we're talking about high performance computing, where large data sets are kind of the name of the game, right? We want to process large data sets, and we want to do it fast. We're going to do anything we can to squeeze out performance from these things. So easy to implement, not particularly complicated, but also not universal in the sense that I can't do it with everything. In a lot of cases, it's going to be overkill, right? In a lot of cases, it's not going to be necessary. Are there any questions? Yeah.
Is it ever just as beneficial to transpose the second matrix before you do everything that you do row by row?
Yeah, so that will help a lot, actually. Transposing the second matrix would give you some performance benefit. You're still going to eventually end up past the size of the cache line, right? So that even if you transpose the second matrix, that would still be an improvement over this, but it wouldn't be as much of an improvement as this one, because this really allows us to access the entire block repeatedly. Going across entire rows probably would not. Yeah, great question. Any other questions? Yeah.
So would this be a good way to gain one of those benchmarks? You could mess with your cache sizes to make a particular benchmark run faster.
Absolutely. Although this is not, some tightly held secret. A lot of people know about this, and it's almost, for the types of systems that we're talking about, supercomputers, this is pretty much par for the course. You're expected, if you're going to be iterating over large data sets, you're pretty much expected to do this. So I wouldn't really call it as much of a hack anymore. Good, great question though. Do you have a question?
Yeah, I guess is this strategy
So for graph algorithms, it depends on how you're storing your graph, essentially, right? A lot of this is based on the idea that the array is being stored in row major order. Even if we take arrays out of the picture and I just have like a bunch of variables or linked lists or anything like that, I can't necessarily guarantee that it's going to be stored contiguously in memory. I can probably assume that it would be and be right, a significant portion of the time. But with an array, I know for a fact that it's all stored contiguously, right? So the answer is yes, but it would require a little bit more information. Yeah, great questions. Any other questions? I actually have the code that I used to do this on the course website. In fact, I think I might grab a copy of that right now because I'm going to use it for the next section as well. So let me just pull that up here if I can. Oh, I don't even have the website open. I thought that I did. Yeah, so here's the Memory Mountain code. I'm going to grab a copy of this. You're more than welcome to grab this and play around with it. It might come in handy for the assignment. It might not. I'll leave that up to you to decide how useful it actually will be. But I'm going to, what am I going to do next? I'm actually going to, well, I grabbed a copy, but I'm not going to use it right now. I'm actually going to move on to the next slide deck, and then I will need to use this in just a little bit. Okay. So all of the rest of what we're going to talk about today pretty much directly applies to the first homework assignment. What we're going to spend the next 2 hours doing is basically kind of a tutorial of what I expect from these assignments, because they are going to be a little bit different than what you're used to in some of your other classes. I usually get a lot of questions on these first homework assignments. You will get used to it. I think while they might be a little confusing at first, in the long run, you will enjoy how they work. So, whoops, wrong button. Here we go. Cool. So I already mentioned last time that these homework assignments are really going to be, what I ask you to turn in is essentially going to be a research paper, kind of. I mean, I'm not going to hold you the same standards as a publication quality research paper, right? That's not what I'm saying. But I do expect you to collect a data set and apply some statistical analysis to that data set, and then tell me what the data means. Tell me what you found. That's what I'm looking for out of these homework assignments. And so I want to make sure that we're all on the same page. I'm going to present what I readily admit is probably somewhat biased, opinionated information about experimental results, and you may hear other people tell you completely different things than what I'm about to tell you. But they're not grading your papers in this class. So this is what I would like to see on your reports. Let's take a look at some. I do expect you to create plots to help you visualize your data, right? Some plots are better than others. This one is particularly atrocious. Can anybody? Made up data. It does not mean a darn thing. It's just, I think I actually literally randomly generated it. But what if, this axis stands for a number of chords and maybe this one stands for execution time? Yeah. That doesn't bother me too much. I mean, yeah, I think that starting at 0 might look a little bit nicer. That's not the main problem that I'm concerned about, though. Yeah. I'm sorry?
You need like a connected block plot for that.
Ah, yes, great. So, I mean, if this axis represents the number of chords, do I really need these lines in between the points? That implies that these points are related in such a way that, if I only had 2.5 chords, then this would be the value. Well, for starters, I can't have 2.5 chords, right? And even if I did, implying that this is the value is, I think, a little bit shaky, a little bit too much of an assumption, right? So in this case, the lines should go away. These are distinct data points, distinct from one another, independent data points, right? All right, let's fix some things. Here's the next iteration of this plot. So the lines are gone. That's good. I've got some labels, which is awesome. So number of cores, execution time, looking better, right? This time I decided to even take this a step farther, and instead of just one data point for each value on the x-axis, I collected 3. Looks like I collected 3. What's the problem now? I don't have a legend, right? Although if I know that these are samples, is knowing that this one is from sample 1 and this one's from sample 3, is that really? So legends are good, and you will need to use legends, but that's not the main issue here. Yeah. It's too much. It's too much. It's too much data. If I have one sample per value on my x-axis, okay, this would have been fine. But if you have more than one, maybe 2 samples per independent variable, you really need to do something with those. You need to combine them somehow statistically, right? So one way to combine these values is to use the average. That's one that people come to a lot, right? So here, we've taken the average, which is great. The average is a perfectly useful statistic. What are we missing now? We're getting better. What's missing now? Yeah. Error bars. We need some way of tracking the variance of these, right? So at this point, it looks like I'm using this value as the end-all be-all for this particular x-axis value, for this particular entry. But that's not really true. There's always going to be some error involved. There's always going to be some variance involved. I want to see some aspect of that variance. That tells me how good the data quality is, right? That tells me how consistent your samples are, right? So we need to use error bars, and this is where I fully admit that I'm going to get kind of opinionated about how to do this. We need to use error bars. For this class, we're going to make an assumption that the data collected is from a normal distribution. That's a pretty hefty assumption that's probably not actually true. But it's better than nothing, and we're going to make some simplifications in this class because, like I said, we're not submitting this to Nature or anything like that, right? We're not submitting this to be published. So the classic error bars would be standard deviation. I do not want to see you use standard deviation for your error bars in this course. I would like to see you use students' t distribution. So students' t is going to be more relevant since we are assuming a normal distribution, which I know I just said is kind of a clumsy assumption, but that's what we're assuming. Students' t is going to be more relevant than standard deviation. If we were not assuming a normal distribution, then standard deviation might be more appropriate. But in this case, we're going to use students' t. So let's talk about students' t. Many of you used students' t before? A couple of you? Good. It's not that bad. I know there's a big fat equation staring you in the face right now. It's not that bad. We'll work through it. So it's based on this idea of a confidence interval. And what I mean by a confidence interval is if I say I have some level of confidence, like 95% is a typical confidence level, how close is our sample mean to the actual mean? So how close is the average of our samples close to what the actual mean would be if I took infinity samples, right? That's what we're trying to use our error bars to measure here. So the computations that you see here, here's our giant equation. Let me tell you what these things actually are. X sub n bar is going to be our sample mean. So I collect a bunch of samples, I collect a bunch of execution times, I average them. Done. That one's easy, right? S sub n is going to be the standard deviation of our samples. Also a very easy thing to compute, right? Lots of languages will do this for you. A is a function of confidence and degrees of freedom, where confidence, like I said, is a value, typically 95% or 0.95. And degrees of freedom is represented as the number of samples you collected minus 1. So if n is the number of samples, which it is, that's this value here, degrees of freedom would be n minus 1. And so n is the number of samples. You see we take the square root of that. And c is going to be our confidence. Okay. And so what you see here, you see this equation is the same as this equation, right? With the exception of the sign, the addition and subtraction. This is going to define our lower error bar, right? This is going to define our upper error bar for our plots. Oh yeah, I forgot to mention for A, there actually is a function in most, in a lot of languages to compute A. It's the T, in Excel, it's TINV. I use MATLAB actually though, which is also TINV, I believe. I don't have it written down in my notes, unfortunately. And I believe if you load a statistical library into something like Java, there will also be a TINV function. It's a fairly common thing to be computed. Google it, you'll find something. So now let's take a look at where we're at with our plots. Looking much better. We've got error bars. What does this actually mean, right? So now you see even our labels, number of cores versus execution time. N equals 3 tells me how many samples I took. That's another conversation we're going to need to have in a little bit. The error bars now tell me how much variance to expect. Again, this is random data. These error bars are actually pretty horrible. But so what this means is that I am saying with a 95% level of confidence that the actual mean is somewhere in between these error bars. That's what I'm saying. We want these to be small. That means that our samples are actually representative of the actual mean. If they're large, that means our samples are not a very good representation of the notice they'll always be symmetric, right? Always, 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 always be symmetric. So this works up to a sample size of around 20 or so. And for this class, that is plenty. I am going to ask you to collect multiple samples. So if you're collecting across cores, for example, like in this particular example up here, for a single core execution, I usually suggest between 3 to 5 samples, which is going to get kind of tedious. Write a script to do it for you. That's what I always tell people. Use your scripting kung fu to write a script to do this for you, so that you're not just sitting there hitting enter, 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 over and over and over again. I'll show you some tricks later about how you can do some of that stuff to help you out as well. But ideally, the more samples you have, the smaller these error bars get, and the closer to the actual mean your values represent. Are there any questions about this? I really want to see you use students T on your assignments. That's what I want to see when you create plots. And you should create plots, and you should collect multiple samples. Alrighty. If you want to use some other plot types, don't feel like you're restricted to just using students T with error bars. Histograms can also be useful to explain, especially if you're going with larger sample sizes. There may be a case where you want to use lots of samples for a particular reason. If you're going with really large samples, then histograms are actually probably better than students T to represent. Just make sure that you specify your bin sizes appropriately. These bin sizes are much too large. Right? The buckets are much too large. This is a lot better. I can clearly see the shape of the distribution a lot better here than I can here. What's the drawbacks of using a histogram versus the example we saw before? I have a bunch of histograms, right? This is one histogram for 4 cores, whereas on this one I had a varying number of cores, right? So if I want to do the same set of data with histograms, I have to have one. Each of these is one histogram, right? That's kind of the drawback of histograms. So I don't expect to see a ton of those, but they might come in handy, so I like to talk about them. And then finally, if you want to do a box and whisker plot, this is for if you have a particularly large number of samples and you don't want to do histograms. You can use a box and whisker plot. Where the median should go here in the center. Some people will say the mean. I say the median. I'm not going to get too angry if you use the mean instead, but it really should be the median. This is quartile 1 down here at the bottom of the box, quartile 3 at the top of the box, and then the minimum down to 1.5 of the inner quartile range, where the inner quartile range is quartile 3 minus quartile 1. Anything that falls beyond that is an outlier and should be listed individually. You're going to have outliers. I fully expect that you're going to have some weird ass data points that pop up every once in a while. Those are kind of fun, I think. Those keep things interesting. Include those. Don't throw those out. Do not throw those out. The only reason I would throw out outliers is if it's due to a human mistake and you know what you did wrong, right? Oh, I ran this with the wrong parameters. That's why it took so much longer than the other ones, right? Okay, then toss it out. If you don't know what went wrong and you think it's a computer thing and it's not due to human error, include them. I want to see them, and hopefully I want you to speculate on why that happened. They're valid data points, right? Cool. And so this allows you to do something like this, right? Where going back to our previous example, each of these would be equivalent to one histogram. This is actual data now. Although it's not my data. I think I stole this from a report that somebody turned in last year. It looks real nice though. Okay, so just to kind of wrap this up, you need to be very clear about what your plot represents. Very, very, very clear. Outliers, leave them in, but be prepared to talk about them. So, some other rules of thumb about the homework assignment, since we're kind of on the topic. I expect you to create plots. For every plot you create, you should spend at least a paragraph of text telling me what that plot is showing me, right? Tell me what that plot means. Having the plots on there is great. You need to tell me what that plot means as well. We're getting very close to actually starting to take a look at the homework assignment here, the homework assignment itself here. If you can't include something in the plot, if there's some information that you collected that can't be included in the plot for whatever reason, tell me about it. Write text about it instead. Write a paragraph. Tell me about it. Okay, let's move on to something a little bit more interesting. Are there any questions about visualization plotting stuff? My programming language of choice for this kind of thing is MATLAB. If you don't know MATLAB, now might be a good excuse to learn a little bit of MATLAB. It is very, very good for creating the plots. I use it to create all the plots that you saw on the previous slide. In the past, people have used Excel, which will work. It'll get you by, but it can be a little bit more cumbersome in my personal experience. But use whatever you like, of course. MATLAB is on these lab machines, so it's already on there. It's not free either. You have to pay like $1,000. So don't buy it just for this class. But all right. The last topic I want to talk to you about today, and then we'll spend some time talking about the homework assignment. Actually, let's take a break. Why don't you take a 10-minute break? We'll pick up around 6:30.
So I had a question that I want to